this unit, we're going to do backpropagation. Backpropagation is the fundamental workhorse of deep learning. To keep things simple, we're going to do scalar programs first, and then in the next unit, we'll handle tensors and vectors. So backpropagation is applied to source code. And we're interested in computing the gradient of a loss with respect to the parameters of the model, the source code. So let's take a really simple example. So suppose the loss is the square root of x squared plus y squared, the norm of the xy vector. So the first thing I'm going to do to put this in a form that's appropriate for backpropagation is to write this as a sequence of assignment statements. We want to think of this as source code. And the last assignment statement here assigns the loss. And the way backpropagation works is first there's a forward pass. We compute the value of all of these variables, just as in an ordinary program. After we've got the value of all these variables, we want to compute the gradient, the derivative of the loss function with respect to each variable. So we start by looking at the last line, line 4. And line 4 allows us to say, well, what's the derivative of the loss function with respect to the variable r? So we're starting at line 4. We say that the derivative of the loss function with respect to the variable r is just the derivative of this expression, which is 1 over 2 root r. So now we've got the derivative of the loss with respect to r. Now we go back one step in our program, and we say, what's the, what I'm going to compute now is the derivative of the loss function with respect to u, and also with respect to w. So I'm looking at line 3, and I'm just going to apply the chain rule. So the derivative of the loss function with respect to u is going to be the derivative of the loss function with respect to r times the derivative of r with respect to u. And that derivative is 1. So when we're going back, the derivative of the loss function with respect to u is just the same as the derivative of the loss function with respect to r, which we computed earlier. And the same thing applies to w. So from line 3, we get the derivative of the loss function with respect to w is equal to the derivative of the loss function with respect to r. And then we keep going back. So now I know the derivative of the loss function with respect to w. I just computed that here. I can compute the derivative of the loss function with respect to y, again by the chain rule. I know the derivative of the loss with respect to w. I multiply that by the derivative of w with respect to y, which is just 2y. So that by the chain rule applied to line 2, I get the derivative of the loss with respect to y. And again, the same thing applies at the first line. And so what I've done is I've computed a forward pass to get all the values of all the variables. And then I've gone backward through the program and computing the derivative of the loss with respect to each of the input variables. The input variables here are just x and y. So at the end of the day, when I get to down here, I get the loss with respect to x and y, which are the input variables. Okay, I love abstractions. Let's do this for a somewhat more abstract, but still scalar program. So the numbers, all the variables in this program are still going to be just numbers, just scalar values. But I'm going to introduce arbitrary functions. So I'm going to compute the derivatives by just assuming that I can compute the derivative of these functions, f and g and h. And we're going to do the same thing we did before, but now in this more abstract setting. So I compute the values forward. I'm computing the gradients backwards. So I'm running through the program backward. So the first thing if I have this final assignment, the derivative of the loss with respect to u is 1. So that's trivial. Then I go back to this thing and I say the derivative of the loss with respect to z, I'm just applying the chain rule, is the derivative of the loss with respect to u times the derivative of u with respect to z. And the derivative of u with respect to z is just h dot, is just the derivative of h. But the derivative of h is taken at the value z. So when I do this, I'm using the value z to get in computing the gradient of the loss with respect to z. And I can just continue. Now I've got the gradient of the loss with respect to z, so I can use the chain rule here to get the gradient of the loss with respect to y. That's just the gradient of the loss with respect to z times the gradient of z with respect to y, which is the partial of g in that first argument. Okay, this is where things get less obvious, a little trickier. X, I want to get the gradient of the loss with respect to x, but x occurs twice in this program. X is x and y, x is the input variable to this program, but it occurs twice. So I can't just naively apply the chain rule here. I can't say that the gradient of the loss with respect to x is just the gradient of the loss with respect to z times the gradient of z with respect to x, the derivative, because the x occurs twice. So how do we handle multiple occurrences of a variable when we want the gradient of the loss with respect to that variable? So what we're going to do is we're going to think of each variable as an object in the sense of C++ or Python. And we're going to think of this object as having a value attribute and a gradient attribute. And the value attribute is the value of the variable that's computed on the forward pass. And the gradient attribute is the derivative of the loss with respect to that variable. Okay, so every variable has these two things, its value and the derivative of the loss with respect to that variable. And we're going to run backward. Now it's a little tricky. I have sort of a formal languages background. You know, I love algorithms. So we're going to define an algorithm that has a loop in it. We're going to loop over, we're going to go backward over the statements of our program, and we're going to have a loop invariant. So what I've done here is I've looked at the last line of the program, which is L equals U. And I'm considering just the program that consists of the last line. And if you just look at the program that is the last line, the input variable to that program is U, just the variable U. I'm ignoring everything but the last line. And for just that last line, the gradient with respect to Z and Y and X is all 0 because the only input for the last line is U. So we set U dot grad equal to 1. And we can do, and in general, we'll have any program at the last line will be L equals some variable. So this is the way we initialize the backpropagation algorithm. And then we start going backward. So we've initialized, these gradients were all 0 initially, but now I'm including this additional line as I go backward in the program. And so now suddenly there's a dependence on Z. So instead of just setting the gradient of the loss with respect to Z, what I'm going to do is I'm going to, the gradient, Z's gradient was initialized to 0. I'm going to add in the component of the gradient of the loss with respect to Z due to this line, this newly added line. So I take the gradient, I set the gradient with respect to Z to be its initial value 0 plus the chain rule applied to this line, the gradient of loss with respect to U times the gradient of U with respect to Z in this line. Now, because it was 0, I've just set, this actually yields a value for the gradient with respect to Z, and the invariant is still true. When I add this line, I'm getting exactly the gradients for the red program. And the red program, the input to the red program now is the variable Z. And then I just keep going backward. So now for this program, if I just look at the red program as I'm going backward, I need to get the gradients with respect to Y and X. But again, I'm just going to add in the component of the gradient due to this line, because X in particular occurs twice. And because it occurs twice, there are 2 places that X is contributing to the gradient. And as I'm going backward, I just add in the contribution due to this line. So if you look here, X dot grad, I'm adding in the contribution of this line, which is Z dot grad times the derivative of Z with respect to X, which I get by looking at the function G and just taking its partial derivative in its second argument. Okay, and yeah. and then I just continue. And then I get the second component of the gradient of x, the gradient of the loss with respect to x due to its occurrence here. Okay, so backpropagation has a forward pass and a backward pass. And as you're doing the backward pass, you're adding into the gradients for the program lines you're looking at as you're going backward. A lot of people who teach backpropagation say that it's tricky, that students have a hard time with it. I think a lot of that is because they're formulating the problem in terms of graphs. If you formulate the problem in terms of a sequence of lines with a well-defined order and you go backward, I think it should be, hopefully, this is rather intuitive and transparent. Thank you.